All right, we're back and we're starting with the cross product. I didn't nearly cover as much as I wanted to with the dot product, but I think as you use it more, you'll gain more intuition for it. And likewise with the cross product, it was hard to know where to start. So I decided to start with a two-dimensional geometric meaning of the magnitude of the cross product. So we'll get to the vector part of the cross product in a minute here. But first I want to talk about what does this value physically represent. So if we have the magnitude of a cross product, that's going to be equal to the magnitude of the one vector times the magnitude of the other vector times the sine of the angle between them. So as you can see here, here's my vector A and here's my vector B. And I have this extra stuff drawn on for a reason, because I'd like to prove to you that the magnitude of A cross B is equivalent to the parallelogram drawn here. So in other words, if I take A and move its tail to the tip of B, and take B and move its tip to the tail of A, or move its tail to the tip of A, you'll end up with a parallelogram. So in other words, these two are parallel, these two are parallel, and what I'm trying to say is that A cross B, or AB sine theta, is equal to the area enclosed within this parallelogram. So if you'll notice, this triangle here has angle theta. So does this triangle, angle theta. Turns out both of these triangles are similar because they're sharing the A vector and the angle theta. So those triangles are exactly the same. So for area, we first have 2 times the area of this triangle, which I'm calling area 1. So this triangle plus that triangle. And then we have this interesting rectangle in the center, and I have that drawn here. I've called it area 2. And so if you'll look closely, the projection of A onto B is A cosine theta. So if that's A cosine theta and that's B, then wouldn't B minus A cosine theta give us this area right here? And so this area right here I've written as B minus A cosine theta. That's I'm sorry, not the area, that's the side length of the bottom side of this rectangle. And then of course, because this is opposite the angle and the magnitude's A, this height is A sine theta. And so A sine theta here. So area 1, the area of one of the triangles, is 1/2 times base times width, or times base times height, because this is 1/2 of a rectangle, and a rectangle's length times width, therefore a triangle's 1/2 length times width. So 1/2 length times width, that's the area of one of these triangles. The area of this rectangle is A sine theta, so this side length, times B minus A cosine theta in brackets, or this side length. Now you'll notice that there's 2 of these triangles, and so if I say that there's 2 area 1s, that means I get 2 times 1/2 times A cosine theta times A sine theta, and the 2 and the 1/2 cancel. Whereas on this side, I have to distribute my A sine theta to my B, and my A sine theta to my minus A cosine theta. And what I end up with there is I end up with AB sine theta minus A squared sine theta cosine theta. And what you'll notice is that when you distribute everything, that on this side from the 2 triangles, you're going to get A squared sine theta cosine theta, and from the rectangle, you're going to get AB sine theta minus A squared sine theta cosine theta. These 2 terms are identical, and this one is subtracting, and so they'll cancel. And what you're left with is the magnitude of A times the magnitude of B times sine theta. And that's A cross B, the magnitude of. And so there we've proven that the cross product represents a physical area, actually, even though in its true form it gives us a vector with a certain length and a direction. But the length of the vector it gives us represents the area. Alright, so the next thing I'd like to talk about is the vector side of things. So now we're not taking the magnitude of, we're actually going to look at the direction that the vector will point. And so let's start with B cross A. B cross A. So you may have heard of the right-hand rule before, and it's important when dealing with the cross product because unlike the dot product, the cross product is not commutative. So in other words, B cross A is not the same as A cross B. So if we're doing B cross A, we point our fingers in the direction of B, and then we curl them towards A. B cross A. And we'll notice our thumb is pointing out of the board. And so what we end up with is our resultant vector B cross A is actually going to be pointing out of the board. To point out of the board, we draw a circle with a dot in it to represent an arrow coming towards you. And so this is vector B cross A. It still has a magnitude of the parallelogram created by the two vectors, but now its direction is actually in the positive, it's in the positive z direction, which I'm going to draw right here. It's coming out of the board. X cross y equals z, and B cross A equals z. So one other important thing to remember is when you take the cross product of two vectors, the resultant, so if this is A and this is B, if this is B cross A, the cross product of two vectors will indeed be orthogonal to both vectors. So in other words, B cross A will make a 90-degree angle with B as well as a 90-degree angle with A. And that's really useful because what we call this sort of a vector is we call it a normal to the surface. And so in other words, if you've created the surface of this parallelogram, A cross B, with this given area, its normal always is orthogonal to the surface. And because B cross A is orthogonal to both B and both A, it's safe to say that it's orthogonal to the surface as well. So that's quite useful, especially when we start getting into surfaces, which we will at some point. Also with planes, it's good for finding normals of planes. Alright, so now you'll notice if I would have said, what if I wanted to find A cross B? Remember I said it's not commutative. And so A cross B, now we curl our fingers and our thumbs pointed down. And so A cross B actually has the same magnitude as B cross A. So the magnitude of A cross B equals the magnitude of B cross A. However, A cross B does not equal B cross A for the purpose that they have a different direction. They both have the same magnitude though. Alright, I need to go over a method. So just like with the dot product, we had a method using trigonometry to find the value. So like in this case, you would just say B cross A, and I know that the length of this is going to be magnitude of B times the magnitude of A times sine theta. Just like with the dot product where we did BA cosine theta, now it's BA sine theta for the magnitude. But just like with the dot product, remember we found a way to find the dot product in a vector form if given components of two vectors. And so I would like to show you that same method here. I'm going to give us two vectors with three components each, just to show the whole process. So we have vector, let's say A, that is 1, 2, 5, we'll say. So it's got 1 in the x, 2 in the y, 5 in the z. And we'll say we have a vector B. We'll make it easy on ourselves. We'll make B have units of all 1 in every direction. And so if I want to know the vector of A cross B, in other words, I don't have to do the right-hand rule now, because this is actually going to spit out a true vector, not just a magnitude, and then you find the direction, like the trigonometric method is like. So we have two components, And what we're going to say is that A cross B is equal to this matrix. The heading is IJK to represent our unit vector directions. And then if A comes first, we write the values of A in the next row. And then the values of B in the second row. If this was B cross A, those would be reversed. And so we take I. This is called a determinant, by the way, and it's going to take a while to get used to. But for the I part, so I'm going to write the I here. For the I part, I'm going to cover out my rows and columns that intersect with I, and I'm going to say I is equal to 2 times 1 minus 1 times 5. So 2 times 1, which is 2, minus 1 times 5, which is 5, plus the J component, which is 5 times 1, so we're following the pattern of going down and to the right, but because we run out of room here, we pop out over here. So J is 5 times 1 minus 1 times 1. 5 times 1 minus 1 times 1. Plus, in the K direction, we cross out our columns and our rows, and K is from the left to the right and up to down. K is 1 times 1 minus 1 times 2. So that's 1 minus 2. And so what we end up with is that A cross B equals negative 3I plus 4J minus 1K. And so this is going to take a lot of practice. I recommend watching other videos to help you make more sense of it. There is a multiplicity of ways to do determinants, like the cross product. I just have a particular method that I like to use, but there are plenty of other methods. So please go and check that out. And I'll see you next video for parameterizing curves.